Yes. Okay. Lauro. Quiet. So it is a pleasure for us to have House of Skuladottir today here to present her talk about the galaxies. Also, took her PhD from Groningen a few years ago. Then she moved to Heidelberg, ENPA, and then to Florence as a postdoc. Among the other things and accomplishments, she is the PI of the foremost four dwarfs community service, and she recently got a PhD again on dwarf galaxies, and it will officially start next. Please, Elsa.
Thank you very much. So my name is Elsa, and I am your neighbor from Florence, and I'm here to talk about dwarf galaxies. So I hope, no, doesn't work. Yeah. Right? Ah, perfect. So the Milky Way is a really enriched environment because we have more than 70 satellite dwarf galaxies. And over the past few years, we have been able to identify many of these thin streams covering almost the entire galactic halo. And many of these are believed to be destructive dwarf galaxies that have fallen into the gravitational potential of the Milky Way and being stripped apart. So we really have so we're really looking at a snapshot in the formation of the Milky Way. We can really see the effects of these small systems. And why do we care? First of all, dwarf galaxies are the most common dwarf galaxies in the world. So I think it makes sense that we want to understand something that is the most common one. But also, we believe that these are the first galaxies to form. They hosted the first stars, and then later they became the building blocks of the Milky Way, and of course, other larger galaxies that we see at larger distances. So the great thing about the Milky Way dwarf galaxies compared to other dwarf galaxies is that they are close. And this is really important because this means that we can look at individual stars. So we can target individual stars in these streams or in these really small dwarf galaxies that we cannot even detect at higher redshift. Here we can look at individual stars, look at them with telescope and get very detailed and high quality spectra. And this will give us radial velocities or line of sight velocities, as they are correctly called, chemical abundances of their stars and ages. So it really allows us to track completely how these star systems formed and evolved. But of course, this is a little bit of a simplification. This is not the type of telescopes that we use. Typically, we need the big ones, the best ones that we can have, because these systems are still quite far away. So they can be targeted with individual stars, but it's still a little bit hard to do because there are significant distances of something like 100 kiloparsecs or so. So we need to put in some effort, but it's definitely worth it because these small systems, they are treasure trove of information that we want to dig out and learn from. First of all, we can learn a lot about chemical evolution from these systems because all of these individual systems, they have their own star formation history, they have their own evolution, and this allows us to break a lot of degeneracies when we want to understand what is the origin of the chemical elements and how they build up throughout cosmic times. So it's really convenient that we have these many systems in our backyards so we can really study them in extraordinary detail. Then, of course, if we want to understand the hierarchical buildup of the Milky Way environment, which I think we all want to do, then we really need to understand these systems and understand what is their role in creating the Milky Way as we see it today. But now I'm going to talk about more specific part of dwarf galaxies that I also think is very fantastic. And this is the fact that they are very metal poor. So here you see these are simulated metallicity distribution functions. So it's basically the number of stars and how they are distributed in metallicity. So these are simulations, but they fit very well with observations. And what we see immediately is that as we go to smaller and smaller galaxies, they become more and more metal poor. And here, just as a reference for the eye, I put the line at 100 solar, or iron of -2. So all of the stars on this side are more than 100 of the solar irons. So these are very metal poor stars. And as you can see, when you go to the smaller systems, they are completely dominated with this very metal poor population. And this is a very interesting population, in my opinion, especially because these guard the signatures of the first stars. So if we want to learn about the first stars in the universe, we can really target these systems and look at the really these are some of the most pristine environment that we can see with a very minimal chemical enrichment. So what do we know about the first stars? Not as much as we would like to know, that is for sure. We know that they formed after the Big Bang, some 200, 300 million years after the Big Bang, and they're only made of hydrogen and helium. And in that sense, they're fundamentally different from all the stars that formed later on, because these stars have heavier elements, what we call metals. And the metals helped with cooling the gas when they were formed. Metals help with cooling the gas and fragmenting it. And without metals, this becomes harder. So theoretical predictions tell us that these stars are likely more massive than the stars that we see today, simply because the gas had more difficult time in fragmenting. However, if stars with mass less than 80% of the mass of the sun were able to form, these should still be alive today. Which means that if these low mass stars formed, you can still see them here in the Milky Way and in the dwarf galaxies around them. In principle, in reality, we haven't found one, not yet. We are still looking, but we have not found one yet. So this brings us to, okay, and the problem is also we have never seen a first stars directly. This is something that has not happened. Everyone is trying to, but it's a really difficult thing to do. We haven't found it in our neighborhood. And also, what we expect to find with James Webb is that it's going to be really hard to target individual stars, individual supernova. It's something that we're not really optimistic that we can actually do. So what do we do? Do we just quit and study something else? No, of course not. We find our way through it and try to find a way to learn about the stars indirectly. So in the most simple picture that we can have is that these first stars formed through a completely metal-free cloud. So it's just hydrogen and helium, and they existed with hydrogen and helium and nothing else. Then, in a gross oversimplification, a lot of chemical evolution happening, and then a new next generations of stars are formed, and they are all chemically enriched to different degrees. And then the good question is, do these stars really exist? These low mass stars, because if you have low mass stars and they live longer than the age of the universe, they should be sitting there in the dwarf galaxies. And all these dwarf galaxies, they're very metal poor, they're very old, they're completely dominated by this really old stellar population. So you would maybe expect to find them. And just to remind you here that here it is very useful to look at this really most metal poor systems, because these are completely dominated by the metal poor end. So if we have first stars, we would expect that the highest fraction of them would be in these smallest systems. Note, not the highest numbers, but the highest fractions. And the fact that we still haven't found any single star like this, can we learn something from this? Because of course we always want to find the most exciting thing, but if we don't find it, what can we learn from non-detections? And this is some of the work that I've been doing with Martina Rossi, who's here, or mostly Martina has been doing it, is that we can use detailed chemical evolution models of an ultra-faint dwarf galaxies to try to constrain what is the mass distribution of the first stars. And the mass distribution of the first stars is really the holy grail of understanding the first stars, because the mass tells you everything. The mass tells you how long the star will live, the mass tells you what kind of elements it will produce, what is the effect it has on the environment, on the galaxy formation, how many ionizing radiation, and all of this. The mass distribution is really everything, really the fundamental thing that we need to know, and we don't. So any bit of constraint that we can do really, really helps. So by applying this chemical evolution model and assuming different mass distributions and different conditions of the first stars, we can predict different numbers of stars that we expect to find. So assuming that, let's say, all the stars are super low mass, then we would expect that a lot of them are living already in ultra-faint dwarf galaxies today. If let's say most of them are really massive, but only very few are formed, then you would expect very low numbers, even lower than this, lower than 1%, etc. So what we can do is compare these different ranges of models to the observation to see what can we rule out at this point. What is the fact that we can rule out? So if we compare the model to the data, how much data we have of the systems that fit with the model, it really tells us that if the mass distribution of the first stars was the same as the one of present-day stars, this means that we should have seen them already. Statistically, we should definitely have found a first star. And here is just one plot from the paper of Marty. And this is just showing the shaded area is just how much data we have right now. And these are different confidence level of an IMF, similar to the one that we expect at the present day. And we can already see that the normal IMF, the one that we have now, can be completely excluded by the model. And this means that the first stars, they really were more massive than what we see in the stars that are forming today. And this is really an important result from Marti Tinarossi, because this is a completely independent probe compared to if you have like really theoretical simulations of how the stars formed, completely theoretical, no observations come in. This is completely from a different angle. So one is just how are the stars formed from a theoretical perspective, but this is really understanding how much we would see today given the different mass distributions function of the first stars. So the ultra-faint galaxies, even though we don't see the first stars directly, we are still learning a lot about the first stars from these small systems. However, what happens if we never find the first stars? We then quit? No, we never quit. It's impossible to quit. It's too exciting. So what we see is that first the first stars formed, then they exploded as supernova, and they enriched their cloud with their unique signatures. And then when new stars formed from this cloud, they keep exactly the chemical products that the first stars left behind. So then we go through our really gross oversimplification again. We have chemical evolution. And then we have today a galaxy that has many different generations of stars that have gone through many different kinds of chemical enrichment. And what we want to do is to find these really unique second generation stars that really on the surface, these are really small, unassuming, really dull stars. They're just sitting there, this being the same for 13 giga years, waiting for us to discover them. And then on their surfaces, they're really keeping the chemical abundances that were left by the first stars. And the question is, can we find these second generation stars? And then finally, the answer is yes. Finally, we have good news. We have yes, because here you can see, so this is the carbon over iron ratio, and here is the iron abundance, which is often a proxy for metallicity. And here, let's focus on the black points of the Milky Way, and all colors are the different dwarf galaxies. And what you can see that as you go to lower metallicities, you get higher and higher and higher carbon. And just to remind you that these are extreme numbers, like really extreme numbers. We're talking here, this is 1 millionth of the solar value. This is 10,000 the solar ratio. So this is a logarithmic scale. So we're talking really, really extreme values. We can really see how the carbon over iron goes completely through the roof as you go to the lowest metallicities.
Recording in progress.
And since this is a signature that we only see at the lowest metallicity observation, and we see that it gets stronger as you go to more and more pristine systems. Observationally, this is really convincing that what we are really seeing is truly the signature of the first stars. And this has been known for quite a while. And this is one of those times where you have an agreement, observations, and theory, because if you have a simple chemical evolution model predicting where you would expect to find the descendants of the first stars, you can see this in blue, while the data is in black, and you can really see that they lie in the region where you would predict the descendants of low energy supernova of the first stars to light. So this is the situation, the way that it has been for, let's say, at least a decade, maybe a couple of decades. We have accepted this, but really, like you can see here, all the evidence has really focused on this low energy supernova. But now let's get back a little bit to the wonderful dwarf galaxies that I'm going to talk about today. And we had this quite a big survey. So we were targeting all of these, these are dwarf spheroidal galaxies, this is an ultra faint. And we were really trying to understand what are the metallicity distribution function and what are the radial velocities, trying to understand the kinematics and overall global chemical enrichment. And what we found is from all of this sample, a few thousand stars, the most metal poor stars in our sample was found in Skuladottir, which is here. It's a really nice galaxy right there. So I looked at the spectra of this star, and just by looking at it by eye, you can already see that it's quite metal poor. So this is a -2 star. This is also already a very metal poor star, something like 100 solar. And then you can really see that these calcium H and K lines, they're really broad even in this metal poor star, but then you can see it gets smaller and smaller until you have this new star here at something like -4. So already just by looking at the spectra, not doing any analysis, you can see that this is a star that stands out, just from looking at the spectra, no analysis. Another thing that you can see from the spectra, just by eye, is that it's not enhanced in carbon. And this is kind of strange, because at this metallicity, all of the stars in the Milky Way, or the majority of the stars in the Milky Way, are quite enhanced in carbon. And the stars who are not, they're all the same. They're all very uniform, they're all very dull. They're all very uniform. So this made me, let's say, moderately interested for this star. I was like, okay, it's very metal poor, but I have a lot of the other things to do. Do I care? Do I care? It's not carbon enriched. So at least I decided to check for the basics. We found out there's an ultra metal poor star, so it's a -4 star. And these are really rare. So it's 1/10,000th of the metallicity of the sun. So it's extremely metal poor. And we have very few stars like this in dwarf galaxies. Then I started looking at the carbon in more detail, and then I found that it's not just carbon normal, but it's actually carbon poor. It has below solar carbon ratio, which is not really at all what you would expect at this metallicity. And just here you can see the lovely accreted spectra in black, and the blue line shows if there's no carbon, and the red shows the best fit. And here is how the spectra would look, or even bigger than this. This is the limit of what we'd call a carbon enhanced star. Basically, if it would look like this, it absolutely does not look like this. It's not carbon enhanced, but it's actually carbon poor. So it's something like -0.3. And it turns out to be the lowest carbon that is measured in any star. And actually, when you combine the low carbon with the low iron, it turns out that it's the most metal poor star that has ever been discovered in any system outside of the Milky Way. So at this point, I was like, okay, I should analyze this star properly. I should do things in a proper way, even though it turns out to be quite boring. We have so few stars at this metallicity. We have none essentially, or very few stars with similar metallicity. And these are really important because whatever signature of the first stars, they should be there. So even though it's a dull star, I will analyze it, make a quick and maybe slightly boring paper, but it should be out there for sure, just to enhance the statistics, if nothing else. So this is what I expected. In the metal poor range, these are the carbon normal stars. So these are a famous sample for those who are in the field. Really high resolution, good analysis, and really good data. And what we see is that all of the stars, the carbon normal stars, they are the same. This is magnesium over iron, they're all the same. And this is where I expected my star. So I would say, okay, my star is just another chiral star, but it just happens to be in Skuladottir. This was my assumption. But then I started measuring, and then my star turned up here. And I was like, solar magnesium at this metallicity is a very strange thing, because at this metallicity, everything is dominated by core collapse supernova, and core collapse supernova create a lot of magnesium. So you would expect it to be super solar. So now this star got me hooked. And I started to analyze everything I could with the accreted spectra. And then I did everything proper like you're supposed to. And then I found out that there were other peculiarities. This star was not what I expected at all. And then when I compared this abundant pattern that I measured with predictions from the literature, I actually found that this is the descendant of a hypernova. So before we talked about this carbon-rich stars, and these are all low-energy supernova. On the contrary, hypernova is a high-energy supernova. So it's the 10 times the energy of the normal supernova. And these have been predicted for decades, really decades, but all the observational evidence that we found were only for the low energy supernova. So we didn't really know if these existed in reality. And just so the blue is the best fit. And here is a low energy supernova, so you can see it's completely different. And here is also a prediction for pair instability supernova, which is another beast that I'm not talking about so much, but you can ask if you care, which is clearly also not a good fit. So we're seeing something completely new. So we're expanding the view that we have of the first stars, that we're not just only carbon enhanced metaphor stars, but it's really something bigger. All this big zoo of different supernova that we see in the present day universe, maybe it also existed really in the primordial universe as well. However, everything that I show, and just to show, I forgot about this one. So this is the abundance pattern, but also where it lies in iron is really where it's predicted. So these are predictions for the Milky Way in a new paper by Joanna Couturideau, who's also working in Florence. And really, this is the metal where you would expect to find the descendants of hypernova. So blue, exceptionally, you would not expect to find any, but you would really expect to find them in this region, exactly where my star lies. And you might say in the Milky Way halo and sculpture is not the same, but we find very similar results in a model of ultra-faint dwarf galaxies in a new paper by Martina Rossi. And also this general parametric model also show that this is really the region where you expect these descendants to lie. So everything really super fits. It's really done deal, more or less. But the problem was that I had not fantastic spectra. I had okay spectra, let's say. It's intermediate resolution, it's X-shooter, 10,000 long wavelength range. But this star is very metal poor, so the lines are not so strong. However, this was exciting discovery, so we published, and then we asked for more data. And then after we published, we got some new data, and then I started to panic. What if everything is wrong? But if everything that I did is completely wrong, and now I have to debug everything, making this big claim, and everything is a disaster. So, but I overcame my fear, and I analyzed the spectra to the best of my ability, and then the result came out. It's a 20 solar mass hypernova. So it's exactly the same. Let's say within the eras, it's exactly the same. So this result is really robust, and we're really finding something really exciting, in my opinion. So now just to show you how the prediction, so I want you to focus here on the lines. So this is sort of, if you have a low energy supernova, you expect to eject a lot of this carbon and a lot of these light elements that are depicted here. But when you have higher energy supernova, you expect actually sub-solar ratios of these two. So here in the lighter elements, it's a really different beast depending on what kind of energy the supernova has. However, when you get to the iron peak, it's more or less the same. It's a very similar thing. So when I got this new star, a new spectra, new wonderful UV spectra for this very exciting -4 star, I started thinking about the other low metallicity stars in sculpture. So already in the discovery paper, we plotted the literature data, and we found some interesting trend. But the problem is that all of these stars are so rare that it's always published one star at a time. So every single star is analyzed from a different person with a different method. So if you have 10 stars analyzed by 10 people and you find a trend, you're never sure if it's because of the different systematic errors or if it's something real in there. So the only option that I thought was reasonable is just to reanalyze everything again. It's dozen stars, so I think it's something that had to be done. And we also had 2 new stars that we had found through other methods. I won't go into the details. So one of the new discoveries is also that we found a new carbon-enhanced metal-poor star here at -3. And this is the most metal-poor star in sculpture that we have found. That there's a carbon-enhanced star and shows this clear difference between the general population and then the carbon of this star. The fact that carbon-enhanced metal-poor stars exist in sculpture was not new, because I found another one. This was actually my first paper, the first paper I ever wrote during my PhD, and we found this star randomly, but it was a much higher metallicity. And this is a weird guy, but I will not talk about him today. So we found this new CMP no star, but this was not really the discovery, in my opinion. In my opinion, the discovery that we found this, the fact that we found this star, that was not the real discovery, in my opinion. My opinion, why not more? Why didn't we find more of them? Because if you look at the Milky Way here in gray, you look at the ultra-faint dwarf galaxies here in yellow, more than half of the stars are carbon-enhanced metal-core stars. More than half of them. So why do we have one in Sculptor, where we have more than a dozen stars? So it's the statistics that are really starting to show a real difference. Why do we have all of those in the Milky Way? Why do we have all of them in the ultra-faint dwarf galaxies, and why not in a dwarf surrounding galaxy? So not an obvious answer to this. So of course I analyzed more elements, and then I found out that it was not only the carbon that was a little bit different. Because if you study light elements, here is sodium, and then you can see sure Sculptor falls within the whatever you have in the Milky Way, but all these high points here are missing. So Sculptor is really following the low envelope here. It's not having the same distribution as in the ultra-faint dwarf galaxies and in the Milky Way. Then I looked at the alpha elements, magnesium over iron, and you see this strange downwards trend here. Like here, this looks like a normal galaxy. Everything is the same in all galaxies. But if you look at these lowest metallicities, then you start to see these unique trends, these very unique trends that I also saw in the literature data, but I didn't trust until I knew that everything was on the same scale, and they still appeared in my analysis. So it was already there in the literature data, but it was just confirmed by analyzing everything again. But if you look at the iron peak elements, everything's the same. So Sculptor is the same, ultra-faint dwarf galaxy is the same, Milky Way the same, and there are more abundances here. I just show a few examples. And if you remember these plots, you remember that the energy of the supernova, it has big effect on these light elements, has a very little effect of these element ratios. So what we are really seeing is that here, Sculptor, these are the average abundance trend over the metallicity range that I showed you. That if you look at these light elements, you see these big differences between a Sculptor and the other systems. But if you go to the more, let's say, iron peak elements, it's more or less the same. Within the error systematics and all of us, it's quite similar. So it seems quite obvious to me that Sculptor experienced a significant pollution by a high energy first star. So Sculptor is really a galaxy that is really guarding this high energy supernova that we haven't really seen as clear an evidence of before. And you can sort of, so I will show you this plot here. There's a lot of things happening, many colors, so don't panic. But basically, if you focus first on the shaded areas, so these are prediction of where you would expect the descendants of different populations to lie. In gray, we have the population of, let's say, low energy supernova. Here you have the, let's say, high energy supernova here in this red area here. And then you have a mixture, something that is maybe enriched both by normal stars, but also by the first stars. And what you can clearly see is Sculptor is here in blue. But if you add the other large dwarf galaxies or the dwarf surrounding galaxies, you see that they seem to also lie here at the low end. While the ultra-faint dwarf galaxies and Milky Way, they're just poof, blowing up in carbon. And if you think about it, at least from the perspective of ultra-faint dwarf galaxies and dwarf surrounding galaxies, it does make sense. If you have a dwarf surrounding galaxy and you have a really energetic hypernova, so a really energetic supernova, the potential well of the galaxy is large enough so it can keep the products of this high energy event. If you have a super small galaxy that's only like this, and you have super energetic hypernova, most of the metals will be lost to the environment. So even if you would expect that some hypernova would happen in ultra-faint dwarf galaxies, a lot of the metals would be lost and you would not see them in the next generation of stars. So this sort of makes sense. And if you look at it in a really quantitative way, it's a little bit shocking. Like if you look at minus 3.4, something like this, everything in ultra-faint dwarf galaxies is extremely carbon enhanced. All of them are carbon enhanced. In the dwarf surrounding galaxies, none of them are. So there clearly is this very clear differences. However, what also surprised me, and surprised me a lot, is why are the Milky Way and ultra-faint dwarf galaxies the same? They are not similar, they are same, like exactly the same, better than you would expect from observational data. like observational errors, systematic errors from different surveys, you would not expect them to be exactly the same. You can see Sculptor clearly is not the same as the other guys. This is obvious. You can see that very clearly in the light elements. But Milky Way halo, ultra-faint dwarf galaxies, almost every single abundance that you look, they're the same. They are completely identical. And you might say, that's just easy. The ultra-faint dwarf galaxies created the Milky Way halo. But this is not the case according to the simulations. Because the simulations say that only 2 to 5% of the stars below -2 are created by ultra-faint dwarf galaxies. The rest come from bigger dwarf galaxies like Sculptor. But we clearly know that the Sculptor did not create the Milky Way because we can just see it directly from the data. So is there here some discrepancy between the models and the data? So this brings me to my first conclusions. So these are all very civilized and non-argumentative. We have from galactic archaeology and the modeling of Martina Rossi, we've showed the first stars are more massive than present-day stars. And this is really important because this affects their entire evolution. We have found this very interesting star that shows the signature of zero metallicity hypernova. So we're really, the box that we have been looking in have been like this narrow. We're only looking at the low energy supernova. This is all that exists, but suddenly we're opening up a new dimension. We're seeing new aspects of the first stars that we haven't really seen before. And it's telling us that first stars are more complicated than maybe we thought. And also that Sculptor really traces the extreme of the energies of the first supernova, because you both have this carbon-enhanced stars from the low-energy supernova, but you also have this hyper-matter-poor star that shows this hyper-energy, the hypernova, 10 times the regular energy, and then less than the typical energy. So it's really tracing the entire energy range of the first stars. Now comes more complicated conclusions. Okay, first of all, we can say with absolute certainty that the Milky Way halo at this metallicity is not made up of Sculptor-like galaxies. There's no way. It's just not. It's proven. We don't even need to discuss it. It's done. However, the Milky Way halo and ultra-faint dwarf galaxies are remarkably similar, and it's not obvious why they are so similar. There may be some solutions to this. Maybe the models are just wrong. Maybe we just need also better modeling to really include these dwarf galaxies, to see maybe if the dwarf galaxies that were swallowed by the halo were different from, for example, Sculptor. So maybe Sculptor is a very unique outlier, and other dwarf solar galaxies have much less data, so it's much less certain what they can say. So we really need sophisticated modeling. This is outside of my scope as an observer, but we also really need better observations. And here is where I shine, because I really like data. Who doesn't like data? But I really like data. So, but if you look at these very interesting systems, like now the entire talk, I've been talking about maybe dozen stars. And already from dozen stars, we're learning so much. We're learning incredible things that we cannot learn from anywhere else, just from a dozen stars. And now typical sample sizes for chemical abundances in this system is like 1 star up to maybe 100. 100 is considered a very large sample in these systems. However, if you look at the plot, these are more than 100 stars. These are like way more than 100 stars. So wouldn't it be nice if we could just get all of them? All of them? Wouldn't that be a super nice world? Imagine if we can learn this one was from 12 stars. How can we learn from all of them? Asking for all of them is maybe a little bit too greedy. So how about all of them that can be seen from the south? That's not bad, no. So I applied for a survey of four dwarf galaxies and stellar streams. And after a 2-year, very competitive and very draining application process, we were awarded something like 500,000 fiber hours in this Foremost. And Foremost is a 5-year survey that is coming on Sky, hopefully next year, it's like late 24, possibly early 25. And the goal of this survey is to target all of them. All of the dwarf galaxies that we see in the south, and also all of the streams to understand which of them were disrupted dwarf galaxies, how they formed, how they evolved, and what they can tell us about the different things. And just to show you the scope of this survey, we will get high quality radial velocities, chemical abundances, and stellar ages for every single star that we observe. So here is the number of stars with 10 elements measured. Here in gray, you can see the status of the today. These gray error bars are decades of hard work. Really, I contributed to this gray error bars, and I know it's really hard work, and it's really decades of hard work. This is what we want to do with photos. So we're completely changing the field. This is a completely new era of this study. So I'm very excited to see when we finally get the data. Of course, we have many scientific key questions. Right now, I've only really focused on the first stars, but there's so much more that we can learn from the systems. Like really a lot more. So one of the things that we want to learn is that how are the chemical elements created and distributed throughout the universe? Where do the chemical elements come from? How are they built up in the universe? How are they distributed? And here we're focusing especially on things like supernova type 1a, neutron star mergers, and AGB stars, or asymptotic giant branch stars, which is a pain to say for a non-native English speaker, but I did my best. And another thing that we want to understand is what are the dynamical properties of dwarf galaxies. We want to understand what are their binary fraction. Are they in equilibrium? Are they being disrupted by the Milky Way? Do they have specific unexpected velocity profiles? We don't know. We don't know until we have the data. And then finally, we really want to understand what are the small scale limits of hierarchical galaxy formation. Because this is something that is really unique. And just because we are close, we can really look at these really small systems that are essentially invisible to us at high redshift. Or even if we can see them at high redshift, we can study them in much smaller detail. But of course, we can study much more systems, so it's highly complementary. So we really want to understand how the Milky Way halo came to be from the smallest galaxies that started to form the Milky Way, and really understand how the halo became to be like it is. But we want to go beyond that, because we also have dwarf galaxies, and we also expect that these dwarf galaxies are made up of even smaller dwarf galaxies. So we want to also look at the dwarf galaxies themselves and try to see if we can find evidence of mergers within mergers within mergers within mergers, if you will. So if there's only one takeaway that I want you to have from this talk, is that dwarf galaxies are fantastic. They really are fantastic, because they're really a treasure trove, and they hold the key to so many fundamental issues in astronomy. From stellar evolution to dark matter to hierarchical galaxy formation, nucleosynthesis, neutron star mergers, supernova, first stars, the evidence and the impact of all of them is started in these very small but important systems. And the second point that is very exciting is that data are coming. Thank you very much for your attention.
There are two questions. Either you shout or you come close.
Yes. I also. So I was also puzzled and therefore intrigued by the comparison with the individual dwarfs and the halo.
Yeah.